respect, I'm going to be talking about buffer metadata. And this topic, as you'll see, in order to process packets efficiently, the packets have to travel along with some information. And we're going to describe how the VPP stack does that. It's not a particularly deep topic. I mean, every packet processing system, the PDK, for example, has buffer metadata. And there's a little bit of subtlety to the way it's done here. Those of you who've written NPU microcode, how many folks have actually written NPU microcode in the room? Oh, cool. Yep, great. So we've got a few veterans, presumably with the battle scars from that. You're going to recognize some of the techniques. None of it's magic. And this stuff, if it's not clear, please stop me, because it's kind of important that folks get this. Joke number one, people who love sausage and respect the law should never watch either one being made. It is buffer metadata. There are techniques in use here that are not, that are not necessarily structured programming techniques, with a great number of forms of training wheels to keep people from hurting themselves. One of the things we don't want to do is to start using the buffer metadata as a city landfill. That the whole idea is to maintain the trade-off between having the information you need to do your work and not causing unnecessary pressure on the cache hierarchy and on the load store unit to suck it back in when the packets are cold. That part of that prefetching paradigm that one looked through in the max swap world applies also to the buffer metadata. That the way things are currently structured, you're not going to have to do any extra prefetching to get buffer metadata, and you want to keep it that way. Following the coding patterns, you can make yourself really sad by doing silly things here. And the per buffer opaque strategy, folks are absolutely going to recognize. I have some ideas how to make that a little bit more bulletproof, which we can maybe talk about a bit. But without further ado, this is a spatial layout picture of an RTEMBUF that contains in RTEMBUF private data the VPP buffer metadata. In other words, you have the RTEMBUF on the top. At size of struct +1, you find the VPP or VLib buffer T, and thereafter it's all tangent to the DMA target. That the VLib buffer T ends up having its own notion of headroom size, so that you can paint a tunnel and cap back, actually into the VLib buffer T from there. That's a pretty common thing. We end up having a couple of handy macros, which are just the obvious, size of struct mumble plus or minus, to translate one to the other. The actual fields in the VLib buffer T, the first thing in there is a signed 16-bit quantity, which is the current offset from the nominal DMA target, effectively, of the data you're processing. As you descend into networking layers, that'll move forward, and the length will be compensatorily decremented. Current length is, again, as it says, the number of bytes between the current data and the end of this buffer. Now, obviously, you can end up with a chain of MBuffs with a chain of VLib buffer Ts. The two structures are maintained in parallel as chains, simply so that long pre-existing VPP code will continue to work. The buffer flags, the trace flag is important. The next present flag is important. The total length valid flag is important. That one's ordinarily set by the drivers. One can imagine a device where you only get per descriptor lengths, and it might need to be set. But at any rate, some of the infrastructure uses those bits. One thing to say is that if you look at it, the flags are a 32-bit quantity, and for emailing back and forth between two graph nodes, it's perfectly fine to use a couple of buffer flags. The log2 buffer flag user gig is so that the stack constant bit positions are allocated, sort of from the least significant bit up, and the user flags are implemented or allocated top down. Again, this is programming for consenting adults. There aren't a lot of training wheels here, so be a little careful what you wish for. Don't randomly overlay stuff. Free list index. Back in the good old days of the VPP native buffer allocator, that was used to do such things as have buffers of different sizes for different devices. You might want to play that game. It's barely used at the moment. Total length, not including first buffer, is exactly what it sounds like. It's interestingly enough, it's the last thing that vlib buffer init for free list actually sets up from a template. The point there is that in order to, when we allocate a buffer, which will have actually come out of a DPDK RTM buff pool, we end up painting a template on top of it at the driver layer. If you look at the DPDK, VNet devices DPDK node.c, you'll see a call to to set up the VPP buffer metadata from what we were able to learn out of the RTM buff metadata. There's a little bit of, well, why are there two of them? And in some cases, it wouldn't be a bad idea to, it wouldn't be a bad idea to sort of do duplicate elimination. On the other hand, we explicitly are willing to build versions of VPP that don't use the DPDK at all, the DPDK Lite image, for container use for a variety of reasons. That trying to actually have a total shotgun wedding between the two, they're not currently doing it in the barn, so Farmer John isn't going to necessarily insist on a shotgun wedding. It's a little wasteful, yes. It takes a few small number of clock cycles to set up the one from the other. And in the transmit path, what would that be? That would be VNet, devices, DPDK, device.c. You'll see the DPDK transmit function where you figure, okay, we're not keeping up both sets of metadata the entire way through the graph, but rather when a packet's to be transmitted, you set it up. There's no reason to go do that if you're just about to throw the packet on the floor, because the DPDK mbuff freer doesn't particularly care if the if the various offsets and so on are done. Another thing I would say is that I would put it, the trace index. That's it's used in the packet tracer. Probably a not terribly interesting topic. Clone count is really a misnomer. It's if non-zero, the device transmit routines will transmit a copy and recycle the original buffer. This is used, for multicast replication and so on, done the old historical way. Turned out way long back, the VPP buffer allocator had a native concept of, when a particular buffer has been transmitted, throw it back on a free list, and you could do multicast replication by using a particular free list that had a callback that would then apply a few edits and recycle the buffer out. The packet generator kind of works that way. Problem with it is that DPDK buffering system doesn't really have such a notion, and as a result, the clone count doesn't mean what it used to mean. And again, it's a little bit of backward compatibility. It is absolutely in plan to start doing, particularly for longish, for long packets, to start using the DPDK buffer clone facility, where you suck the variable portion back into a a header. It's the way that buffering system wants you to do business, and we'll in the very near future do it. We're about to start a proof of concept of IPv6 segment routing spray use case, which involves replicating packets. And if they're big packets, you really don't want to be copying the data. Well, for a proof of concept involving 3 of something, and nobody's going to sit there with an Ixia and pound on it, it's okay to just copy the data. But very rapidly, we know we're going to want to go to an mbuff clone with a variable header kind of setup. So that's on its way. Now, the Opaque array of 8 by 32 bit data is actually what amounts to subgraph metadata. It's, I'll show you in VNet buffer.h. If folks want to rack that up and look at it, you'll see that there's, a union of a variety of stuff. This is the real node-to-node local significance buffer metadata that you might in a lookup node be scribbling down things like adjacencies, adjacency indices, where you do a lookup and then the rewriter is going to use that piece of metadata. Now, Opaque 2 is pretty much a mistake. Somebody said, well, God, I need a whole cache line for my whatever piece of code I'm trying to pour on top of this stuff. I think the use case went away, but the piece of junk is still there. So at some point, step one, change name to, I think I'm going to delete myself to, see if it compiles. If it compiles, the field gets the bum's rush. Don't know how else to put it. Predata is the rewrite space currently set to 128 bytes, and data is the aligned DMA target. It's not by any means guaranteed that the hardware will be programmed to DMA there. That I know the ThunderX chip tends to do a 6-octet offset with the idea of aligning the IP4 header. And you can ask yourself the question, but it's not uniformly and on all hardware platforms the case that the first octet DMA'd off the wire will end up in data sub-0. Be nice if it did, because frankly, especially given an 8x4 M-try walker of an IP4 fib, aligning the IP4 address is kind of a yawn, but that one I happen to know is due to use of silicon blocks that were already in hand, and holy bleep, you don't want to be redesigning silicon, and obviously the device driver can deal with it. So again, I've sort of spoiled this slide a little bit. In the VNet buffer opaque T, in the opaque union that's used all over the place, the first two elements are always the receive and transmit software IF indices. The transmit software IF index, if you look in the device driver, again, if you look in VNet devices node.c, you'll see the TX, the TX slot always set to twiddle 0. That means don't know yet, because you haven't done a lookup, you haven't decided what interface you're pitching the thing out. Now there's an interesting piece of overlayment that we'll look at later in terms of the IP4 fib, which is to say, lookup stages feel perfectly free to interpret that particular metadata field as a VRF ID or fib index. And as a result, if you want to do route leaking cases where you've done one lookup and now you say I want to encapsulate in a tunnel and forward through a different VRF, what you do amounts to about a one-liner that says, mumble sub vlib tx gets the fib index you want to actually work a lookup against. When we look at the IP path, you'll see it. Yeah, as I said, I should read my own slides rather than just doing this off the top of my head, because I end up saying the same bloody stuff except in a better order in the slides. So the driver level, as I said, does sets the software IF index to the RX physical interface, and the TX slot is always set to twiddle 0, and the lookups, boy, I just ought to read my own bloody slides. At any rate, the IP46 lookup guys, as it says, it'll interpret twiddle 0 as meaning lookup in the interface's parent VRF or fib, however you want to say it. And otherwise, it's an explicit go lookup in this fib right here, please. Yeah, the deliberate route use, deliberate route leaking cases, or tunneling a packet received in a non-default VRF and forwarding using routes in the default VRF, MPLS over GRE works that way. As I said, janitorial work is needed to clean up the opaque. So the IP union subtype passes especially adjacency indices from the IP406 lookup to the rewrite stage. The RX adjacency is the source RPF check hit, meaning, okay, here's the adjacency that made me believe that a packet could actually have been received from a particular subnet on the interface it came in on. Everybody know from source RPF check here? I'm sure most people have heard of it. What it amounts to is you don't want some clown on a particular interface just being able to spoof any old address, any old source address. And one of the obvious checks is, look, I know the interface address, I know the subnet mask. Is it possible for this packet to have arrived on that interface according to the configuration? And if the answer is no, the packet goes in the floor. That it keeps, it's one sort of spoof check that any router worth its salt will do. The TX adjacency is set up to be the effectively the rewrite the rewrite index. It's set by the destination address lookup. Current config index is an IP feature path configuration handle that's processed by IP4 and IP6 input. We can have a look at how that kind of configurable feature arc works at a certain point. It's not the first thing you want to look at, but it's an interesting detail to say if you want to apply IP input features in a very specific order, there's just an easy way of listing them in one place and then having the features be configurable on or off. The IP adjacencies themselves have an interesting degree of freedom, which is the lookup next index, which allows programmers to send packets that match a certain destination, address, and mask anywhere in the graph they like. The idea being, when you've done a fib lookup, you end up with an adjacency that can direct the packets anywhere in the graph they like. And this is really cool because you don't have the lookup engine knowing at all about what's about to happen, that you can say, oh, I want next to go to the encapsulate in this magic tunnel type node. And such and such a subnet needs to be reachable via tunnel. What you put into the fib is lookup for the prefix / mask, and an adjacency whose lookup next index points off to the please go encapsulate me guy. It's really an extraordinarily general way of doing it. The IP4 and IP6 fibs both do it. The classifier has essentially a variant of the same game. The theme is just go program the table the way you want the data to flow in the graph. When people talk about graph node registrations and how do I get my node to collect packets, one of the mechanisms you can use is say, okay, any packet aimed at a particular subnet mask goes right over there. Or any classifier hit for a particular n-tuple that you may have classified against goes right over there. And plugins can play this game. Basically anybody can play this game. You just need to construct an adjacency. The other slightly dirty thing you can do if you want, and pleading guilty to having done it before, is to say, okay, I'll just go install a vanilla IP adjacency and then go fix the lookup next index. That's all pretty damned easy to do because you do a lookup, you look in, you're going to get back out of the lookup engine an adjacency index, you go fiddle with the adjacency, and if you did everything right, it works. If you didn't do everything right, well, you do the math. Again, I'm wrecking my slides here. If adjacency lookup next index sends packet to your node and your node leaves IP adj index of vlibtx alone, you can send the packets to the rewrite engine sometime later. So you can actually put little or even extensive feature subgraph arcs into the IP, IP whatever lookup rewrite chain by just simply having an adjacency that diverts the packet off into a subgraph arc that then eventually shoves the stuff back into IP4 or IP6 rewrite. And the rewrite nodes pay no attention to the lookup next index because it's not really their business. They look actually in the rewrite header. And again, it's a very typical, sort of barrack manipulation that results in no performance hit if it's not used, and it's about as slick and fast as you can get a way to divert traffic out of the IP lookup, IP rewrite, ship out to the interface path. So this thing here, this little eye chart, it actually doesn't look so bad. Wow, I'm thrilled. That actually came out better than I ever would have guessed it was going to. this is an intersection analysis of the VLAN buffer opaque T union to say, okay, Ethernet, for example, is going to use octets 8 through 11 as the start of Ethernet header. The IP world uses it as the RX adjacency. And you can imagine that if you sort of draw a line down here and you say, okay, well, node A and node B actually use the same fields, oh boy. This is the classic case of doing per packet context in a network processor where you don't really have enough space and you end up unioning or overlaying in some cases single bits in that context structure, and now you hurt yourself with it because node A in an ABC path sets something, node B rect it, node C believes the rect value. You have to be pretty careful with this stuff. Now, static analysis of this is probably just about impossible because you can't know what doing a live versus a live data analysis is really hard. I can imagine with a bitmap and some some arithmetic and a debug image actually saying, oh, this node just pickled something. Because it's possible to scribble down, okay, I just set something, to add some macro. Well, I can imagine doing an intersection analysis. Noticing, what's a good example? I'll bet you that some of these guys have actually ended up, it looks like the multicast guy was shoved way to the right, strictly so that it wouldn't land on the IP adjacencies. That if I remember the situation, that was kind of the one time in the last 3 years I burned myself with this stuff. You just have to be a little bit careful not to, for example, make your union type populate octets 8 through 11. Or 12 through 15, 12 through 15, and then go throw the packet at the IP rewrite engine because it's going to believe something that you've gone and spoilt. Typical NPU programming, I can tell horror stories about it. But at any rate, the intersection analysis really says that this thing isn't packed very hard at the moment. Because you'd expect it to be just all gray, where almost every octet, had 6 users of it, and it's not that bad. L2 stuff, you mostly don't do L2 and L3 on the same packet at the same time. Now, it's perfectly permissible for L2 to hand a packet to L3. IRB, for example, will do that, but the live variable analysis says that that's okay. It's just that there are no training wheels on this bicycle. If you mess up, you're going to end up hurt. So that's really, end work zone. So Keith, anything you want to throw at me, or does that make some sense?
No, it looks
Oops, I bet I'm going to be sorry I did that. That's one. Hopefully it'll just actually come up.
Yeah, because we're fine on the SWIF index because it's ahead of the union, right? That's why it's
Yeah.
right.
Yeah, well, those 2 slots are oh boy. Yeah, probably. I've done this before. Hopefully we'll get back to where we belonged. This is the point at which Jesus may have wept, and we may be recreating the Vagrant VM. But meanwhile, yeah. So, oh yeah. Well, I'm not going to say what was coming to mind, but it had to do with juggling. Or that joke Ward was telling this morning. All right. Well, hopefully the VM will actually come back and be compos metis in a minute. But anyway, are there any general questions about the metadata before I launch into the IP fibs? Nope. Could we grab a mic, please? Where are the mic grabbers and throwers? Oh, there we are. Hey, Ali, thanks.
Thank you. So the question is, what you just presented with overlapping of structures or the use of the fields in the VLEAP Opaque. Is it somewhere documented or it's just your knowledge?
Oh, in other words, how do you avoid hurting yourself?
Yes.
What's the good way of saying it? There currently isn't much to prevent you from hurting yourself. I guess the question is, in a simple case where you have a feature subgraph arc that ABC, if you want to pass data from A to B and B to C, and you know that you're not going to be sending the node to a place that's going to consume something you're overwriting, it's currently a manual analysis, but it's not terribly tough. Generally, if you want to use the IP rewrite engine, oh good, this is eventually going to finish. If you're going to use the IP rewrite engine, you have to stay off the IP adjacency handles. You have to stay off of those. Generally speaking, if you want, the safest possible thing is to shove your data all the way to the end and back up. That's the least, statistically, that's the least likely. I really do intend to to do a little bit of wrappering so that people aren't going to hurt themselves with this. It's just a matter of getting the time to type it in. Whereupon it'll say, dude, that variable you just stepped on, you've actually killed something that you're about to use.
Yeah, the problem is with dynamic paths. With different sequences, because you cannot know beforehand how it would be used by somebody.
I mean, the reason I asked for a show of hands about NPU programmers is exactly, this is exactly a standard NPU technique. It's strictly for performance and to avoid bloating up the memory footprint, and you got to be absolutely careful about it.
So a simple memory management question. So with each vector, at the end of the vector, you processed all the packets in that vector, right? So all memory associated with packets and such is free.
Yeah, you basically hand it back to the PDK
Right.
RTM buff and
so
buff
it's all
allocator.
clean. Every
Yeah.
time you start with a clean
Yep.
clean memory. Okay.
Yep. No, that's a good one. Okay. Others, because I'm probably getting to where I could actually.
Just while you're kind of filling the space, mate, I think part of the question was documentation too, and isn't there a nice kind of for each buffer opaque union subtype macro at the top of the buffer H for each of the unions, where we kind of document?
That's working on a different dum-dum problem, which is that you accidentally got the opaque union to be bigger than the amount of space it's overlaid against, whereupon you're going to scribble off the end of it. Now that mistake is statically checked, and you won't hurt yourself that way anymore, I hope. but the dynamic recycling of live data is not being is not currently checked. It's not an awfully hard algorithm. Every time I've hurt myself with it, which is probably once a year, whether I need to or not, I've said, damn, I should make an afternoon and go fix that so it never happens again. Because it's the lifetime analysis really isn't that hard. You just need to decorate. You'd need to decorate which union types you've used, and if that sequence discloses an error, then you just sort of say, dude, you just hurt yourself, and you may be getting lucky, and it may look like it works, but ... probably it really doesn't. So now, with no further ado, IP, and before anybody says it, yes, I did get the message about the frickin' font, so to speak. Well, of course, that doesn't mean I can type today or mouse today, whatever it is. Anybody remember how big it was before it started being reasonable? Is that enough, or you want one more? Okay, if that's cool, then let's, without further ado. Okay, look up. Okay, this is the main IP4 lookup engine, and you'll recognize that the dual loop for explanatory purposes, it's not necessary to look at the dual loop because it is exactly what you'd expect. So what do we do here? Okay, after prefetching yada yada, we go find the packet. In this case, it's called P0. This is one of the oldest graph nodes, and we were thinking packet rather than buffer at that point. So what we're going to do here is to go figure out which fib we're using. We start off with an initial negotiating position of the software the RX interfaces default table. If you've seen the debug CLI, there's a set interface table blah 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 guy. Well, that set interface blah 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 table ends up populating fib index by software IF index, so that when you get a packet from that interface, we can rapidly rederive the fib. Now, in the case where, as I was saying earlier, buffer metadata, software IF index, vlibtx is twiddle 0 the way it will normally be in a straight up case, you just go ahead and use fib index 0. Otherwise, you say, okay, somebody told me they want fib index 3, not fib ID 1, 2, 3, 4, 5, but fib index 3. So code that populates that slot has to be a little careful about it, because this code is just absolutely unsuspicious. It's the speed path. It can't be checking everything known to mankind. So it just goes ahead and believes you. And don't fret so much about that or about the, is this, that, and the other thing. What you're going to see is this 8x4 M-try walk, where IP4 fib M-try lookup step is walking down a fib. The trick here is that if you run into a slant 8, you really only need to do one step. For speed, what ends up happening is that rather than going on to a new ply, it'll just recycle the current one. So you actually sort of do the same reference 4 times instead of once for a slant 8. For a slant 32, you actually descend all the way down. Now, what's the right way of saying it is? All right. Right, okay, locally respond, all right. So what you really end up doing, and this is a piece of belt and suspenders here, where you actually go check the lookup result to make sure that the side bet tables that are not used in forwarding agree. Every so once in a while, you'll find that assert might go off, and if it does, it's bloody well best to figure out why. The result of the fib M-try lookup is basically an adjacency index, this adj index 0. Again, 32-bit handle, it's a vector. It's actually a little crazier than a vector. I'll get into the adjacency allocator and how we optimize to share adjacencies across multiple fib entries. Let's take a pause on the adjacency sharing. One thing you say is, okay, look, you might have 1 million routes, but how many rewrites are you really going to have? They're bounded by the number of dest max. That if all of those routes are really going out a default gateway, you probably need this many adjacencies, even though somebody may have been annoying enough to download 1 million slant 32s. That they're all going to the same next hop, so you need this many rewrite strings. Adjacencies are fundamentally rewrite strings plus a little bit of graph trajectory steering. That lookup next index guy I keep yapping about. So, and here's the well, how do you actually make the adjacencies lookup next index be where the packet goes? Well, it doesn't get a whole lot more straightforward than that. Now, multipath adjacency is a little interesting topic here, where you say, oh, if it turns out that you end up running into a block of adjacencies and the adjacency has a block count there, what you end up doing is you go do the flow hash. The flow hash is somewhat configurable. See mumble flow hash config there. That says, I want to flow hash on source, on dest, on a combination of things. If you look at it in detail, you can work out exactly what it's willing to do. It'll save around the flow hash in case you want it back later. But the idea is a block of four, a block of four multipath adjacencies equal, four equal cost multipath adjacencies will end up, just being n equals 4. So you simply say adjacency index, plus equals, plus equals the hash and, mumble minus 1. Turns out that the adjacencies are always supplied in power of 2 blocks. Nothing terribly complicated. So you're not doing a mod operator. You're doing an AND with mumble minus 1. You scribble down in the TX adjacency, in the IP TX adjacency, the adjacency you've decided that you're using because the rewriter is going to want it back in a minute, and increment the counters. And you remember I went through this long song and dance about the speculative execution in this graph node, but this is fundamentally the go push packet forward in the graph by 1 or by 2, depending on which arm of the single or dual loop world you're looking at. So that's the lookup step. Now, aside from cases where you actually shove the packet to your own graph node and do whatever you want and tunnel it or so on and so forth, let's talk about what happens next in the standard path, which is rewrite. Okay, rewrite transit. There's really you have to look at the code in excruciating detail to get the subtle distinction, but. Okay, rewrite inline, as you might guess, and again, let's just look at the single loop because there's no particular point in looking at the dual loop. Rewrite inline at this point in the game, is going to extract out of the adjacency index in the standard fashion. It's going to be the TX adjacency. Go get the adjacency. Here we finally have decided we're forwarding the packet. We do the TTL decrement, and this rewrite one header guy takes the adjacencies rewrite header and applies it. It's a little bit hand coded and tuned for rewriting an Ethernet header T. One of the bad mistakes that was in the code base for years, you say, well, why isn't this faster? And you suddenly realize that rewriting an Ethernet header was being done with 2 8-byte writes, that if you think of you're rewriting an Ethernet header in place, and you've got 14 octets and you're sort of doing a backwards rewrite, two bytes that are not significant spill into the previous cache line. Oops. And immediately cause an utterly unprefetched cache miss. That's mea culpa, my fault. Eventually I saw it, and it's like a head slapper. It's like, my God, that is so bloody stupid. And it was worth 3 or 4% for about 2 lines of typing. Unfortunately, this stuff is like that. You look at it cross-eyed and you lose 3 or 4%.
We're bringing a lot of good points. What type of tools you used to see the visibility into this type of cache?
Oh, that I personally am a perf top kind of guy, where the scenario I use is I'll pound the thing till I get a vector size that's not, I've been yapping about there being, kind of a 3-region curve. There's kind of the dead asleep region, then there's a nice linear region, then there's oops, hits the wall. I try and be towards the top of the linear region, which for most workloads is if you get a vector size of 130 or 140 is about right. So you've got it working at, working about as efficiently as it can, but you're not seeing funny effects. Then you run perf top and you say, oh my God, why am I getting this gross stall right there? And it's more art than science after a while. It's been staring at the stuff forever. Now, in terms of tools, certainly perftop's a good tool, vtune's a good tool. Vtune is specifically good for understanding second order complicated stuff you can't see with a straightforward just how often am I seeing a PC. If you got a bloody completely missing prefetch, perftop will tell you almost instantaneously, because what you tend to get is a function where all of a sudden one first use of a load or first use of a load or a store point ends up being 25% of the runtime of the entire routine. That a lot of, in a lot of cases, the code almost doesn't matter. What really matters is what matters is the load store pressure that a graph node's putting on. And, I'm a perf top guy. Damian has any number of any number of things that he uses for for similar-ish things to do some tuning. Yeah, you wanna grab the mic, and if you've got favorite tools.
Well, yeah, I'm also mainly on perf top, and beside that, I was playing a bit with using the PCM counters on Intel CPUs. So yeah, basically perf top with specific event ID. So not really clock cycles, but that you can basically specify the L2 cache miss, L3 cache miss, and such stuff on the perf top. And sometimes VTune, but mainly in perf top.
Yeah. Yeah, and as Damian pointed out, perf top is also handy for more than just clock cycles. I tend to think I tend to think in clock cycles. Now there's an interesting game that you get into, which I call prefetch whack-a-mole, where what'll end up happening is you'll say, oh, why look there's an instruction that's using 5%. Well, I'm not really prefetching that, and you prefetch in one place, and something else will pop up at about 5%. When you start, and you're running around, it's like playing whack-a-mole. There are not if an infinite number of prefetches were available, you could probably cover all the latency to back to the memory hierarchy you ever wanted to. Well, life isn't like that. And true NPUs often have at least a couple thousand outstanding prefetches before the next prefetch will block. Intel, the CPUs, as I understand it, and you guys correct me if I'm wrong, and basically you can get like 16 outstanding before you run out of something. Used to be 8, now it's 16.
And then it's also priority, right? If something else is coming, it's not guaranteed, right?
Yeah. Yeah, I mean, and again, it's heuristic, it's black magic, it's why I have no hair. So, what can I?
First top is the majority of the tools.
Yeah.
Okay.
Yeah. Any rate, so rewrite one header. Let's actually go look at that because it's in VNet rewrite. Right. Let's see. Oh, actually, how about rewrite.h? Yeah, now, let's see. Let me see if I can prove the point. Damian may have actually rewritten this, so it wasn't. Source, yeah. I mean, it looks to me like you went and did this very carefully. Did it over. At one point, it was go rewrite 8 plus 4 plus 2.
Yes, what we discussed yesterday, right, or 2 days ago. We would like to see if we can really a bit more optimize this part and use the AVX2 or something to really reduce number of instructions, because this is a really critical part.
Yeah, yeah, and this is absolutely critical, because every packet that isn't flushed eventually goes through the header rewriter. And the code's simple, it's short because it kind of has to be.
Dave, sorry, quick question.
Yep.
I see that you're using a built-in memcopy and all, right? So is that a totally compiler-specific memcopy? Or is it portable, or what's the use of it?
Damian?
Yes, so actually I already have the patch ready to basically incorporate DPDK memcopy for all VPP functions. But we are trying to keep the code ready to be used without DPDK for some special cases. So we will need to find a way how to basically include memcopy without, even in cases when we don't use DPDK for building VPP.
Yeah, and given that the most likely size there is probably 14 in all cases, certainly the highest performance case that you constantly care about is the adding a no VLAN tag Ethernet header. So again,
14 is not going to matter. You might look in the snab switch source because they've just done the same AVX memcopy stuff. So.
Yeah, I mean we are BSD licensed, so we can just take the code and keep the license, right?
So, so at this point in the game, backing up into the rewriters, it goes in, applies the rewrite, it does a little MTU check. Then what else do? You set the software IF index, which is meaning you set the interface where things need to go. Now next 0, I'm pretty sure next 0, right? Rewrite. Oh yeah, all right. Okay, this is very much the case where it fishes. Now here's another case of being able to steer packets, where now you've done presumably a lookup, you've done a rewrite operation, and now you're going to send this packet in the graph where rewrite header.next index takes it. This is another degree of freedom. It's basically another node with some steering logic out the back of it. What might you want to do here? Well, say you're doing you've just applied a tunnel and cap out of the fib, and now all of a sudden you realize, okay, that tunnel and cap not only is going to need another IP lookup done on it, but also it needs a fix-up pass, because we've said, okay, here's what's a good example? MPLS over GRE, some tunnel and cap. You splat down an IP4 frame in front of an existing frame, and now you've got an interesting issue, which is that pre-canned rewrite string doesn't have any concept of how long the packet is. So the standard gig is you go compute yourself a rewrite string for a 0-length packet, do the checksum. Then you do a fix-up node whose main purpose in life, irritatingly, is to go worship at the let's go fix the IP4 checksum gods altar and set the length. And now that you've changed the length, you have to go fix the checksum or the header's invalid. So IP4 checksum, incremental updating is the bane of my existence. I truly wish it hadn't happened. The history there is that back in the ARPANET days, back when the time of my first job at Opaque and Newman, you're transmitting IP over serial links with no error correction, no hardware error, nothing, and it's really bad when the IP length gets to be way longer than the actual frame length. And if something, if you get a lightning strike in the header, that's why there's an IP4 header checksum. IP6 did away with it. They did some other things that were nuts, but I wouldn't want to get Tony Lee mad at me by complaining. Well, actually, I wouldn't care so much, but Tony and I are old frenemies in a way. But the story there is. IP4 packets, you can paint on a rewrite, but you actually have to go fix the packet length and fix the IP4 header checksum. All this sounding familiar to everybody? Okay, I'm seeing lots of people nodding. That's good. At least your necks are still working. So a pretty typical tunneling scenario, just to talk through it for a second more, is apply an unrouted IP4 or IP6 datagram and then go throw the results back at IP4 lookup. In other words, you'll paint on a rewrite that's 450000 packet length, mumbledy for some tunnel and cap. Then you throw that at IP4 lookup to go say, well, how the hell do I get to the dest address in that packet? And again, it's a directed graph. It's not acyclic that you will have gone down, 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 down. You hit an adjacency that says, oh, he wants a tunnel. You paint on the tunnel and caps. You go back to lookup. Well, now you're going to aim at a partner, and that won't go down that same path. So it's a sort of almost it's a single recursion by another name, where you'll do 2 trips through the IP lookup engine. Now the IP lookup engine is relatively fast. You'd say what, 50 clocks plus or minus? To do one with assuming the tables are a certain size, yada yada. That's not a bad model. So a tunnel and cap, tunnel and cap processing is inherently more expensive than just straight IP4 or IP6 lookup and rewrite processing. That's the way life is. So if you say you can get 10 or 15 Mbps through a single core of racetrack forwarding, you may be looking at 8 to 11 Mbps if you start tunneling, because that 50 clocks starts to add up. I mean, you think about 10 million packets a second call it nominally a 2 gigahertz processor, how many clocks, how many clocks per packet do you have? And, you start saying, 200. And if you throw 50 in there, okay, maybe it's really 400 clocks a packet to do that rate on a kind of a first run Haswell these days. But even so, that's the second trip around the IP lookup engine is not completely trivial. Now, could you paint on a fully resolved rewrite? And this is going to bear on some questions later. Could you paint on a fully resolved rewrite? Yes, you could. You'd still have to do the length and checksum fix up, but it would save you a trip around the lookup track. Is it worth doing that? Well, maybe. The point at which you start having routing topology changes where you really want to throw the packet out a different interface with a different rewrite, aka through a different adjacency, all of a sudden you now have potentially 1,000 or 100,000 tunnels. You've got to go find all those rewrites and fix them rather than fixing a single rewrite. It's purely control plane complexity versus absolute performance trade-off. VPP in a lot of places will tend to do flattening. In other words, when you see MPLS over GRE, you may not be doing a full layer-by-layer decomposition. You may register for for a single destination port and kind of cut through saying, oh well, it's a flavor of GRE. So first we go to a GRE node, yada yada yada, as opposed to saying, oh, I know pretty exactly what this is. Let me just cut to the chase. That again, these are all trade-offs, and I wouldn't claim that for all current and projected future use cases, the trade-offs we've made to date are perfect. The good news is rewriting one piece of this thing doesn't turn out to really involve unwinding a whole pile of spaghetti code. That it's pretty good that way. It's relatively well orthogonalized, and it's not too terribly problematic to do that. So, questions on that stuff? Keith, you look like you're trying to make up something to fill the dead air.
Anything at all. I just didn't want to rat-hole this dude.
No, go for it.
Please, rat-hole me. No, I was just thinking a little bit more about what you were saying with the building out a more sort of complete end cap, which is going to be susceptible to topology changes, right? And then touch up and clean up stuff.
Yeah.
Which, to me, based on kind of my background, sounds like a control plane problem, which could be handled if you had a highly performant control plane focused on that idea, working in tandem. You could do something like that potentially, but that's what I was kind of thinking through. It'd be very specific, but because there's a lot of, when you're computing routing tables, right?
Yeah.
You have a lot of information. I know there's been other work that's been done on having standby tables for argument's sake, right? If you have enough space, you have an active table, you could calculate multiple ribs, right? And then we could push down a bit that was pre-built.
Yeah, that's a, we've been. Yeah. Yep. You want to? Yeah, it's. Yeah, I mean, one of the things our colleague Clarence Fisfis mentioned is, look, for VPP to be really used in kind of core router cases where you may have a million routes, a million BGP prefixes, 1,000 IGP prefixes, and 20 or 30 interfaces, the chances are really excellent that if you get a topology change, it's really going to, if you play your cards right, it's really only affecting a couple of those 20 or 30 last level guys. The thing you don't want to do is three trips around the IP lookup track, because that just is going to get to be where you're relieving the control plane of responsibility for doing intelligent things and being fast at the cost of a ton of data plane performance. And
I just wanted to comment quickly on this. So actually I started looking into doing kind of very light version of RIB on top of the FIB to address exactly that problem. So we currently have a situation that multiple sources can program FIB, and if you have interface down and interface up, you will basically lose the route, because interface down event will of course remove the adjacency from the interface. So idea is very simple, to basically keep the database of routes and even keep the database of different routes from different sources with different metric going to the same destination. And then in case we have an interface up and down event, basically just pick the second best route, which possibly points to the different interface, and basically have the convergence. So not touching really the fib, but putting a very small layer on top of fib, which will basically dynamically update the fib based on the events coming from the network and also events coming from the external configuration interfaces like API or CLI or even ARP and such things.
Yeah, that, again, there's a, as with any piece of this stuff, there've been, multiple trade-offs made a particular way. We've generally gone with more, flattened, with a more flattened fib, one that's not recursive particularly. And we're going to unwind that some and allow the control plane programmer to say, okay, if you want to reach 1.2.3.4 via some other IP address, we're willing to let people not flatten at that point in the game if they want. The problem being, you're going to end up having to do literally multiple trips around the lookup track. And although the lookup the lookup method is reasonably performant, it's not something you want to encourage people to do in this straight up, stone simple case where you're where you're doing 3 or 4 neighbors and you really don't have, you're really not doing anything complicated with routing topology acquisition. That in some of the orchestrated VM cases, you see really, a routing table of possibly n equals 100. And at that point in the game, you just want to flatten everything because it's way too simple to reinstall the thing from scratch to save those extra trips around the track so you get some performance out of it. But, this set of trade-offs wouldn't claim that the thing's perfect. Again, VPP is walks a fine line between being high performance and being easy to change and being relatively well orthogonalized. But I wouldn't swear that for every use case, I swear we haven't gotten it right. But it does a decent job for most of them, probably.